All right. So the first one here, we have dark chocolate, 10 identical pieces, and we have 3 different meal times. So you can think of this like breakfast, lunch, supper. Put in your 2 walls, and then the 10 balls would be where those pieces of chocolate are. So there's 10 balls, 2 walls, a total of 12 slots. 2 of those will be walls, which gives us our 12 choose 2. On sorry, I thought there was a second part on number 1. There's not. 3 positive integers that sum to 10 and a set, so order doesn't matter. And these really you can just list out. I like to start off with maybe the highest number you could possibly have, which is an 8. Then you could have a 721. You could have either a 622 or a 631. Once you get to 5, you do 541 or 532. 4, could repeat. Each time I'm choosing the highest possible first number, then the highest possible second number. I guess I reversed that on the 6s. 4, 3, 3 would also work. And then 3, notice we couldn't get that to reach 10 if we put them in where the first one is highest. And that's just to organize our list to keep it straight. The order doesn't matter, but a 334 would be the same as a 433. And so for my own sanity, I'm just keeping them so that the first number was highest and then next and so on. So this gives us our 8 numbers. And then if we have that list, then number 3, and you could also use the chart for number 2, by the way. How many 3 distinct? Well, here, this one doesn't have distinct, this one doesn't have distinct, this one doesn't have distinct, and this one doesn't. So 4 are distinct, 4 have duplicate numbers in them. So the answer there would be 4. Here we just have a simple subtraction on number 4. On number 5, so a tempting answer on this one is, let me go to the next page, is to think, okay, we know that each person needs on a team, so we choose the 2 partners for one person and then choose 2 partners for the next one and maybe do something like this. The problem is we don't know that everyone's on the team because of that ref. That ref is what throws a little twist into this problem. So that's why my solution has us choosing the ref first and then doing the rest. Now, if we didn't choose the ref first, we could choose our first team of 3 and then our second team of 3 and finally our third team of 3, and then the final person would be the ref. What's going to happen here is the 3 people we choose here in one solution might be the same 3 people we choose here in another solution and vice versa. In other words, we'd create duplicates, and since we have essentially 3 factorial ways that could happen, we'd have to divide those duplicates out. So this would be a correct solution, or you could do where you choose the ref, and then of the remaining 9, then you have a situation like, well, you know all the remaining 9 are on a team, so you choose your 2 partners for some person and then choose your 2 partners for another person. So these should be equal. If you find out those aren't equal, let me know. 6, so we have the alphabetical order and then these indistinguishable clones. So here I was really trying to, as soon as we start talking about people, the assumption is they're distinguishable, and I wanted to have a way to get indistinguishable mixed with distinguishable here. So why is it 13 choose 3? So think about, we have our 10 in alphabetical order, and let's just say person 1, person 2, person 3, person 4, all the way to person 10. these are really like our 10 distinct categories, if you want to think about it this way. And you would put the walls in between each one, right? But the issue here is it's not really that you're putting the alien on top of a person. You're putting them in between people. So really, we need to count the spaces, not the people themselves, as our boxes, as our things that we're putting things into. So this might be space. What's a good way to note this? Space 1. Space 2, so this is like person 1 here. So space 1 is before the first person. Space 2 is in between the first and second person. Space 3 all the way down to you'll eventually have space 11, which is after person number 10. So if you think about lining the people up, and then focus on the spaces in between the people, including the space in front of the first one and the space behind the last one. Then you see we have 11 different categories, which gives us our 10 walls. And then the 3 balls are the alien clones that can slip anywhere here with these walls. So this is why we end up with 13 choose. Actually, 13 choose 10 might be a little nicer because we have these 10 divisions between the 11 space categories. It's the same number, but 13 choose 10 might be a little more cleaner. So here, the only thing that's going to happen is we get rid of space 1, so it's not an option to be in front of person 1, and space 11. It's not an option to be behind person 10. Well, then we just have 9 spaces left. This gets rid of these 2 walls. So now we only have 8 walls and 3 balls, the identical clones. So, so this should give us 11 choose 8 or 11 choose 3, whichever way you want to do that. 3 mod 10, 3 is just 3, and 10 mod 3, what that means is what's the remainder of 10 when we divide by 3? That's just going to be 1, so we're going to add those 2 numbers and we get 4. Let's see, green die, red die, blue die be 10. So if you think about it, there's 3 ways to get distinct die values that'll add up to 10, and that's right here. And why do we care if they're distinct? Because then we have 3 colors and 3 numbers, so 3 factorial. So for example, the 136 could be green, red, blue, red, blue, green, red, and so on. There's 6 different ways that these could play out. When there's duplicates, when there's 2 of a number, which could still add up to 10, like we see here, then you just need to choose the color for the odd one out. Choose the color for the thing that's not the double. And so there's really 3 ways to do that, and then the other 2 are determined. So that's why there's 3 ways each for this. And then a third possibility might be that all 3 numbers are the same, but you couldn't add up to 10. 10's not divisible by 3. Here you cannot use the chart because the die are limited to 6-sided, so it couldn't go up to, say, 8 or 7 for that matter. So because of that extra constraint, it's better just to focus on it step by step, or cases, 2 different cases here. The 10, I mean, if it were just not getting their own gift, then it'd be a derangement. But when you throw in this neighboring kids thing, the derangements things breaks down, and unless you write a computer program, I'm not sure of how to handle that. 3 identical 6-sided dice. So here we have very similar to the partitions that we had before. except there is no 8 and 7 on a dice, so you really only have the other 6 options. Here, 3-digit natural numbers. Do the digits sum to 10? So here I kind of describe the situation. So these are the different digits. So digit 1, digit 2, digit 3. You're going to have two walls there. And then, I guess we've talked about freezing balls when each category has like a minimum amount of balls, but you could also freeze in other ways. In this particular case, we're just going to make sure that the first one's not 0. So we freeze one of our balls, and that takes away one of these balls. And these are just making sure that everything adds up to 10. So 11 choose 2 once we do the walls and balls, but if you think about it, if we would place all 9 in that first category where we've already frozen 1, then we'd end up with 10 balls in the first digit, and digits can only be 0 through 9, so that would give us a nonsense answer there. We're not going to have that problem in the other 2 digits because we've already frozen 1 in the first, so we only have 9 to place in the other 2. We're not going to have to worry about hitting 10 there. 3 positive. So I don't think I'm even going to talk about this. One's a very advanced one. If you can get it, that's wonderful. You can try to follow the solution. 14. So this is, again, similar. We have to be in increasing order, which means we're going to take the ones here without the dots right here, because we have to have different digits. And then there's only one way to put these in increasing order. So specifically 127, 136 for this one, 145, and 235. For each set of different digits, there's only one way to put them in increasing or decreasing, for that matter, order. Non-decreasing, basically this just means we can have duplicates now. So very similar to what we just did, except since we can have duplicate numbers, now we can do numbers like, did we say what? Non-decreasing. So each of these 8 solutions would have one way to put them in order in non-decreasing. 118, 127, 244, and so on. So same answers as number 2, just a different way of looking at it. 16. So we're just using it straight from the chart here. Indistinguishable items, indistinguishable boxes, empty boxes not allowed. Sum, since there's no restrictions that we have to use each letter, we just have 3 choices for each of the 10 letters. If we did have to use all of them, then we could take the 10 places and put them into 3 boxes, S, U, and M, with no box empty. And so we'd have to go to the chart there. I think that's a Stirling number. Here, 3 trick-or-treaters. Again, this one's just straight from the chart. So we have our distinguishable items as houses, and the people themselves, which in general will be distinguishable unless they're identical alien clones. And here we have our Stirling number with a little extra. That's coming straight from the chart, though, even that little extra part. Okay, here is a little different than 17 because they have to be in alphabetical order, M's, S, but we don't have to use all of them. So here again, we're going to have that walls and balls where we have M, S, and U, and we have our 2 walls in between the 3 distinct categories, and we have the balls that we're then placing in there, the 10 balls. So this gives us the 12 choose 2. And then finally, here's just a permutation. It does matter. We're not just whether or not you get included or not as one of the 3. There's also a further division of which position do you get, and that's why we're using a permutation instead of a combination, 120.